quick review of last time. Not sure what I drank this morning. Here's the probability formula we came up with before for binomial probability. Got it. Everybody fall over. Oh boy, all right, so if you weren't here, that is Egyptian hieroglyphics right there. But what does n represent in this? Total number of things. What's x? The number of successes, good, because that's what can vary. Out of 10 people, you can have one person that likes to chew gum, 2, 3, whatever. Number of successes. What's the little p dude? Probability of success. So why does this make sense? If x is the number of successes, how many p's should I have? X of them. It's beautiful. This is a little algebraic thing that represents the rest. If I have n things, and I take x of them to do something, how many's left? N minus x. Pick a man. But everybody gets freaked out about that. And q, of course, is the probability of failure. What's true about p plus q?
1.
It's got to be 1. Right, two types of people in the world. People that believe people can be divided into two groups, and people that don't believe they can be. That was just for what else? Now this is a little bit hidden sometimes, but what else has to be true about p? The successive. Every time I do p, p, q, q, like we did last time with the left-handed people, we did p, q, 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 q. What can't happen between them so that I keep writing the same letter? They have to be independent of each other, or else I couldn't use q every time I had another failure because it would change, and that would so suck. So in order for this formula to be true, the probabilities have to be independent. These events. Okay, I like it. So if all those things are true, you have two possible outcomes, success and failure. Success doesn't have to be a good thing. They add the one, the events are independent. Then you can use this formula. It's a beautiful formula. Oh, tears. Okay. All right, I like it. So that's what we did last time. So here's the part that we haven't done yet. Every time we have a new distribution, a new way of giving data. So if somebody says to me, standard deviation, yeah. If somebody says to me, 87% of people are tired of hearing about Russia, then that is a way to give me data. It's not a list of data. It's not XP of X. It's just one thing. Holy shit. But then I can build all this stuff off of it. There still has to be a quick way to figure out the average, the mean. And this is the best formula. You already saw it on that little handout. But let's see why this makes sense. Stay with me now. Let's see, I'll pick on, well, I can't really pick on him. I always pick on Shaquille O'Neal, even though it's sort of like a different era now. I know he was a Celtic for a while. He's mainly a Laker, so I hate the Lakers. Shaquille O'Neal. Everybody knows Shaquille O'Neal? Some of you guys are like, who the shit is that? Let's say he made 30% of his free throws. So let's be generous. If he made 30% of his free throws, everybody with me? And what would his success be then? In this case, it makes sense. It would be making a free throw. Is everybody with me? And he takes 20 free throws. How many would you expect him to make? So that's the average. If he makes 30% of his free throws, and he takes 20 free throws, how many would you expect him to make? How'd you get 6? 30% of 20. All right. Doesn't that just make sense? If he makes 30% of them and he takes 20, more than likely he's going to make 30% of 20. Now, is he always going to make 6 out of every 20? He's always going to make 6 out of every 20. No. So what does that really mean? After several successions of 20, he's going to average 6. Or else his percentage wouldn't be 30%. I mean, it kind of all goes together. So that's why this formula is so stupid beautiful. I love stupid as an adjective. It's the number of things times the percentage. Of course it is. A percentage of the total. That's the formula for the mean. Now this next one is a little bit, well, it's a lot harder to explain in terms of the math that most of us knows. But the standard deviation is beautiful also. Standard deviation is that. I like it. Now I'm thinking about this right now. There's one thing from chapter 2 that I didn't really cover in lecture, so I didn't really put it on the test. There was a bonus question related to this. So I want to do it right now because it kind of relates to this. Before I say this, do you remember when I was talking about if you flipped a coin 500 times, how many heads would you expect? Flip a coin 500 times, how many heads would you expect? 50%. Half of 500 is 250. So if you flip a coin 500 times, so what's 500 in terms of a variable? In terms of a letter? N. And here the probability of success would be 50%, right? 0.5. I like it. So I love this. See how the phrase expected value makes total sense to be the average? How many would you expect is how many you would get on average. 250. Now, if you flipped 500 coins, I think I've already made this joke, but number one, you got to evaluate your life. But number two, if you got exactly 250 heads, that'd be a little bit freaky, to be honest. You expect it to be somewhere around 250, right? Some range around 250. Okay, I like it. So, this is where I want to figure out what that range is that I expect them to show up in. Is everybody with me? Does this make sense? It's like, what would be unusual then? Would 240 heads be unusual? What do you think?
Yeah.
Is that really far away from 250?
No, not too far.
Not too far. So what's missing for the far? How do I measure distance in statistics? How do I measure distance? No, come on. How do I measure distance in data? What do I use to measure how far apart things are?
Standard deviation.
Use the standard deviation, so it's a z-score that tells me how far things are apart. Okay, let me stop here. How are you guys doing? You all right? So standard deviation is the tick marks on the ruler. Z-score is what I get when I put the ruler down. It tells me how far apart things are. So how far apart are 5 and 6? Are they close? You don't know. If the standard deviation is 1, they're 1 apart. That's pretty close. If the standard deviation is 0.001, they are light years apart. They're crazy far apart. So when I say how close are two things, your answer should be, I'm not sure until you tell me the flipping standard deviation. Right? Maybe. Okay. So here's the thing from chapter 2 that I didn't make a big deal of yet, because it's actually become more applicable very soon. So this is from chapter 2. This is the idea of the empirical rule. So if I have a normal distribution, so what's it look like? What's it look like? Can you do it in
Symmetric.
Symmetric, sure, but there's a lot of things that are symmetric. That's symmetric. Bell curve, I like it. Right? Normal curve is also another name for the bell curve. Kick ass. So it looks like this. Wee-haw. It could be skinny, it could be fat, based on what the standard deviation is. But here's something interesting about this. If I go, I'm going to put z-scores down here, right? If I go 1 z-score down and 1 z-score up in a normal distribution, I will always catch 68 It's actually 68.26, but 68% of the data. Why does that kind of make sense? Well, where's most of the data at? In the middle, right? So one thing you could say is, what if I made the standard deviation bigger? I would get away from it. But if the standard deviation's bigger, my steps get bigger. Your data can't get away. I'm always going to catch 68. If my standard is smaller, I'm always going to catch 68%. I like it. Okay. And if I go one more step up and down, I end up catching, somebody know? 95%. Good. I got some people that read. And the rest of you are like, shut up, man. I got a lot going on. I understand. I didn't cover this in the lecture. You're fine. So go one more step out. I catch 95%, which means how much do I not catch? 5%. So if I knew the average height and the standard deviation of heights, I could figure out between two steps, what's the heights? Everybody outside of those heights. Are there a lot of people out here?
No.
So I would say that that would be unusual. Because what's the probability somebody's out here? 2.5 on each side. How the hell did she get that? Well, this is 95 in the middle. 5% total, so 2.5% on each side. There's only 5%. So I don't know if you know this. Heights are normally distributed. They are. And just to give you some numbers, I think the average height for a man is 69 inches with a standard deviation of 2.5, I think, something like that. Stay with me, stay with me. So see why I keep doing this thing, making you draw the line, put the mean in the middle, go up and down standard deviations. Why do I keep doing that? Because that's a very basic skill to know to do a lot of these kind of problems. So what's in the middle here actually? 69 for this, right? What would this be here? Go one step up from 69, you end up at?
71.5.
Go one more step up?
73? No. 73.5.
No.
74.
74, there it is. So every time I step up, I'm adding 2.5, right? Because how big is each step? 2.5 inches. So if I go down,
66.5.
so 95%, now this is for men, American men. Right? New Zealand men would be different, Icelandic men would be different. But for American men, if you went between 64 and 74 inches tall, you would catch 95% of them. So why are the doors as tall as they are? So that only a small percentage of men have to duck to get in. And women, by the way. There are some women that are up here too. But on the whole, men are the taller ones on average, right? So why do they make the doors that tall? So that only a very small percentage have to duck their head to get in. You with me? So if we're all hobbits, we'd probably be much smaller doors like you do in the movies. If you've never seen the movies, I don't really understand it. Is that decent? Is that cool? So, officially, you can see why we define unusual to be more than 2 standard deviations away. Did I turn this dude on? Yeah. If you are more than 2 standard deviations away, you represent 5% of the possibilities. That's very unusual, would you not say? So if somebody was more than 74 inches tall, 74 inches tall is how many feet inches?
1.7.
So that's 6 foot. I love you guys. 6 times 12 is 72. So this is 6'2". And this would be 60 divided by 12 is 5. So this is 5'4". All right. So if you're 5'3", or if you're 6'3", then you are unusually tall or small, tall or short. Okay, maybe. You guys semi with me? A little bit. How do they determine how wide to make airplane seats? They've had to make them a little wider recently because Americans are growing in the hip region, right? So they take the average, they go out a step, so that very few people have to buy 2 seats or have to complain or something. You guys with me? That's exactly how they determine. They say, what are we comfortable with? How many people are we comfortable with complaining? That would be these people, or in some cases, these people, right? So that's how they determine how big or small to make something. Okay, maybe. So, coming back to this thing. This thing right here. What is the mean for this situation? Flipping a coin 500. And we already determined what that was. You guys remember what's the average number of heads I expect?
250.
Yeah, 250. Now, what's the standard deviation?
250.
It's about 12 point something. 25. Yeah, it's 11.1. I don't know. I got the 11 part. I don't know the rest of it. Anybody going to help me out? Nobody? You're on your own, math boy. Come on. Let's see them neurons fire. 11 point. Anybody going to help me out? What's the square root of?
11.18.
11.1. 8.
03.
03. I like it. All right. To cover your ass on test, if you get exactly like 03 or something, so if you put a 0 there, you know, because it's got to be at least 3 places, so it kind of puts it in my face that you considered that. You guys with me? If you don't, I'm not going to take points off, but just do that just to cover your ass. So if officially unusual starts 2 standard deviations up and down, unusual is more than 2 standard deviations from the mean. So the mean in this case was 250. What's 2 steps up? 2 steps.
72.
Yes, 1 step, and then another step would be 272 point.
And 36.
Yep. Right? How the hell did we get that number? Everybody see how I got that number? If you didn't, there's at least 8 other people that don't. You could say something. Either hero. All I did was take 250 and add 2 of these. So 22.36. Now subtract 22.36. Subtract 2 standard deviations. Go down 2 steps. So 22.36 subtracted from 250.
227.64.
Beautiful. So officially, statistically speaking, if I flipped a coin 500 times and got 280 heads, is that unusual?
Yes.
Where's unusually big start?
272.
So if I got 280 heads, is that unusual?
Yes.
Yes, because it's outside this range. So we've talked before about unusual. We talked a little bit about, in fact, we talked about this exact situation, I think, before. What would be an unusual number of heads? You know.
Right.
Now we have a technical definition of it, which is kind of nice, but also a little misleading. But still, this is pretty decent as far as catching stuff. Now, what's got to be the assumption here is this is normally distributed. Later, we'll actually figure out this is normally distributed. Not too much later from now. Okay, maybe. So if you got the mean and you go up and down 2 steps, that is an estimate for where unusual starts. So if I flipped a coin and got 228 heads, is that all right? Is that unusual or not? 228 heads. Technically, it is not unusual. It is in here. So this is usual. This is freaky. This is unusual. Out there is unusual. In here is usual because it's close to what I expect. If you saw somebody who was 7'8", do you see that every day? Can you imagine 7'8" right now? That is a tall dude. I saw, anybody know Manute Bol? Anybody know that name? Manute Bol. Anybody? Anybody watch any basketball at all? Anybody watch basketball from 15 years ago? He was an unbelievably tall, I think it was 7'7", I can't remember exactly. 7'6", somewhere close to that. He was on a Southwest flight. I wasn't on the flight with him, but when I got off my plane, I saw a group of people, and then I saw him sticking out of the middle. you know. So you do a double take, don't you? If you see somebody who's 7'6", you do a double take. Why? Because it's unusual. Because it's not something you see every day. If you saw somebody that was 4 foot tall, that wasn't a kid, right? 4 foot tall, grown man, grown woman, would you do a double take? Yes, you would. I don't, unless you just work with a lot of shorter people. I don't know. Oh yeah, I work with them. I'm on that show. Little, what was it? I can't remember.
Little big person.
Little people? Okay.
Yeah, the roll-ups from Oregon. Yeah.
Warwick Davis. Life is short. Okay. There it is. So I've established something we're going to use later. I put the raw score here. Raw score means the actual data value. And underneath in parentheses, I put the z-score. You guys see that? That was 2 steps up, so there's 2 standard deviations up. That's the z-score, 2. Z-score, -2.
Always needs it?
Yeah, all right, let me say this. I love that question. It's perfect. Right now, that's how we're defining unusual. If you worked in a nuclear reactor, not in the reactor, but if you worked in a nuclear power plant, do you think your level of unusual that gets you off the seat and gets you worried and makes you check things, would that still be at 2 standard deviations away from normal? Mine would probably be like 1 or even less. The minute that needle goes into yellow or something starts to approach yellow, I'm up. I'm like, right? So in different situations, later in this class, we will talk about when your level of unusual might need to change and how does it affect what we do. So in certain cases, you want your unusual level to start sooner. Get your ass up and go, what the shit? Okay. And other times you're like, I don't care until it's way the shit out of there. And then I'm a little worried. Yeah. Okay. That was a lot. I agree. We just did a lot. So the main thing to get from this is the mean and the standard deviation. And I wanted to show you a few ways it could be used. So let's try to finish this thing out. Part D on this paper. Put it up here. I got my own copy. Let me make it so it shows you. Oh, this dude, did he give up on me?
So the z-score, just to refresh, is really that number that's 2 out and anything past is, it's established. Oh, okay.
Yeah, your mouse. All right, so I'm talking about this one and this one.
Can you put the line?
Oh yeah. Let me see if I can do this. All right, go ahead and try to do those D and E. Don't have a calculator, I'm sorry. Didn't bring any. This is annoying. What are you guys getting for the mean?
6.688.
Good. 6.688. So out of 44 people, I expect 6.688 of them to smoke. 44 San Diegans. Let me make clear about that. So it averaged that many. So if you pick 44, you might get 8. If I pick 44, I might get 5. And some other people, they would average to be 6.688 eventually. So is it impossible to pick 44 San Diegans and get 30 of them that smoke? Is that impossible? No. Good. Almost your answer almost always to the impossible question is no. Right? Probability leaves the door open for a lot of shit. Right? Okay, maybe. It would just be remarkably unlikely. Yes, thank you. I want to make that clear too. So is it impossible to go into a casino and do 3 of the, you don't even do that anymore, you just push the damn button, and get like 3 of them that give you the jackpot in a row? Would that be impossible? No. I have people that tell me, yeah, that's impossible. Never happened to me. Doesn't mean it's impossible. Shit. That's not impossible. Is it unlikely? Oh, hell yes. Very unlikely. Not impossible. I love it. So what do you guys get for the standard deviation? I've been caught up to you guys. Here's how I do standard deviation. Ready? Take the answer, because that's already 44 times 0.152, and then multiply that by 0.848, blah, blah, blah. It's 2.381. 0.381, is that what you guys got? Yeah, okay. All right, so there's the mean and the spread. So how do I use that to figure out what unusual is? What do I put right in the middle there?
6.
Kick ass. Then I go 1, 2 steps up and 1, 2 steps down.
11.
What is it? 11.45?
45.
Sounds about right. And then 2 steps down. 1.926. So would it be unusual to find 15?
Yes.
It would be unusual. Would it be impossible?
No.
No. Would it be impossible to get all 44 smoke?
No.
No. Because more than 44 San Diegans smoke. So it's possible to randomly pick. But would it be likely? Oh, nowhere near. Holy shit. Is it impossible for me to have a class where everybody's last name starts with the letter Q? Is that impossible?
No.
Of course it's not impossible. Has it ever happened to me? No. That doesn't mean it's impossible, but it's stupid unlikely. It's crazy unlikely. All right, I like it. I like it. Okay. So 15 is definitely unusual because it's way outside of what's expected. This is the range of what's expected. I hope this just jives with what you know. You already know that if you flip a coin 10 times, you're not going to be weirded out if you don't get 5 heads, right? You're not going to, I got 6 heads, holy shit, I got 2. Right? Because the range for that, it gives you a little bit of allowance. If you flip a coin 10 times, you get all 10 heads. That's a little weird, isn't it?
Well, you just be suspicious of it.
You go, okay, let me check this sucker out. Is that impossible? No. Is it impossible to get 5,000 heads in a row?
Yes.
Is that impossible? No. It's not impossible. Right? Is it unlikely? Yes. If you calculate the probability, your calculator will go 0 because it can't count that many places out. Right? In fact, you guys know how to do that. You guys know how to calculate. If I flip a coin, Is that what I'm talking about? Yes. 500 coins, 500 times. What's probably they're all heads?
50%.
What's probably the first one's heads? Probably second one's heads. How many of those are you going to have in a row? Is that mathematically equal to 0? No, it isn't. I don't care what your calculator says. Is that 0? What's the only way a fraction can be 0 is if the top is 0. What's the top? 1. What's the bottom? Stupid big. So let's see what the calculator says. I'm very curious. 1 divided by, what's it say?
This is overload.
Poor little dude. Overflow. Cannot compute. Yeah. So it freaks the shit out, which is understandable because 2 to the 500 power is stupid big. So 1 divided by it is stupid small. So I knew either it was going to say 0 Or is going to go, dude, I can't, no. So if we do 50, let's see if it's able to. No, Jeff, you actually have to change the number. Let's see what it does if I do 50. Delete. Yeah. What does that mean?
Scoot it back like 16 times.
Times 10 to the negative 16. Yeah, so 0.00016 times 8. So even getting 50 heads in a row is like crazy unlikely. Okay, maybe. Is that decent? So people have really incorrect ideas about the difference between unlikely and impossible. That's why certain things happen and people are like, it's the end times. No, there's a chance something weird is going to happen every day. In fact, it's less likely that nothing weird happens today, especially nowadays, than it is for something weird's going to happen somewhere. Okay. All right, that's enough, Jeff. Let's get back to it. Okay, so that's this guy. When I ask you if it's unusual, this is what you do. Up and down 2 steps and see if it's caught. Do you see now why I kept doing that whole, how much do you catch within 1 step? I wanted you to get used to creating this kind of thing. Okay, method to the madness. All right. So if there's no questions on that sheet, I'm going to get into chapter 5.
What about the more questions?
Sorry? What about? Oh, sorry. What you got? Good.
We have 2. First of all, 82.
We're in chapter 4?
Section 4.3.
Okay, cool. All right, perfect. This one confuses a lot of people. This is chapter 4. Doesn't matter what section. Just go to number 82. Sure. This is the one about the babies. The babies being born with significant hearing loss. So there's 2 per 1,000 babies. That's how to interpret that. The probability of a baby having hearing loss. In fact, that's a baby that is in a healthy baby nursery. Kind of sounds bad. Instead of a gross baby? I don't know. What's up with the nursery? Is the nursery okay? All right, so the number climbs, here we go, intensive care nursery, that's better. The number climbs to an average of 30 per 1,000 babies in intensive care. So the probability hearing loss in a baby, healthy baby. Probably hearing loss, intensive care baby. 30 out of 1,000. Then it asks you this. People use the wrong numbers in the wrong place. Suppose that 1,000 babies from healthy baby nurseries are randomly surveyed. Screw this. Find the probability that exactly 2 babies are born deaf. So what does it say? 1,000 babies. How many successes do I want? In this case, the success is a baby that is deaf. 2. What's P? This is where people mess up. What's
0.002.
Where'd that come from? From up there. I love it.
Mm-hmm.
Probably that a healthy baby is going to have hearing loss is 0.002. So what's Q?
0.998.
Beautiful.
Also this one.
So this is a beautiful little review of the probability formula for binomial situations. That would be probability of X. So I've got how many babies total?
1,000.
So out of 1,000 babies, choose 2 of them to have hearing loss. So how many of these do you want?
2.
2. And how many of these do you want?
990.
Yeah, cool. And what happens when you try to do that, or
No, I wasn't sure.
Just to make sure you're on the right track?
Because I tried a different way, which is wrong.
I always have people that just say this is the probability or something. There's This is a binomial probability. There's 1,000 babies, so it's n. There's a probability of success, probability of failure. There's a number of successes they want. So it's a little more complicated than just saying this. This is probably one baby has hearing loss. What's the probability that I get 2 babies out of 1,000? That's different. That's not 2 out of 1,000. The probability that I get 2 babies when I look at 1,000 babies that have hearing loss. What's that probability? That's more complicated. Maybe. So again, that was number 82 in chapter 4, 4.3. If you haven't done that one yet, a little preview basically did it for you. Oh, okay, this is the one where 4% of people actually have the flu when they call the medical advice line, right? Has everybody got this?
Because I didn't get the answer from the book, so...
The book is wrong sometimes, which I personally love
They
because
have a
it's
different way
easy
of
to catch
calculating
cheaters.
binomial distribution.
Say again?
Like on the calculator, they have a different way to
I know.
get.
Yes, this is
So I
true.
was lost. Like,
Well, don't worry about that shit. You do it the way we do it in class.
but it didn't give me the same answer.
I don't care. It's let go of it. I like it. Now, to be honest, it should be the same. Let's see if we're interpreting this question correctly. At least 4.
So x bigger or equal to 4, right?
Yeah, so it's probably that x is bigger than the 4. This is number 85, still in 4.3. Here I have n is what?
25.
25 people call the medical advice line. The probability that somebody actually has the flu
It's 0.04.
is only 4%. So the probability they don't have the flu is,
0.96.
and I want how many successes?
Big.
4
At least
or
4
5
or
or
more.
6 or 7 up to 25. I like it. So how many times would you have to use the formula if you did this directly? 4, 5, 6, 7 up to 25. What's the opposite of this?
0.
No. What's it leave out?
3.
2.
It leaves out 3,
Okay.
2, 1, 0. So this is 1 minus the probability that x is less than 4. So you do the probability x is 0. You set the formula. X equals 1, x equals 2, x equals 3. You do all those, add them up, subtract it from 1. I'd much rather do the opposite situation. What's the opposite of at least 4? Less than 4. 3, 2, 1, 0. So if I do this probability and do 1 minus this, it will be the answer to their question. Whenever the opposite situation has less stuff for me to do, I'm going to choose that one. Yeah. Now I know the book shows you something that I will eventually show you, and that's the binomial CDFE, whatever. Right? This is about the time I always have somebody say, well, the last time I took statistics, I didn't quite pass, but my teacher let us just put the stuff in them. Like, that's probably why you didn't quite pass, because the teacher's screwing you over. You understand things better when you don't just let the calculator do everything for you. Okay. Now, depending on how much you round, before you get to the end, your answer might be a little off from what the book says.
No, but I did it completely wrong because I knew that there are 3 probabilities before 4, but I didn't think to...
Oh, there's 4 of them, yeah.
4.
3, 2, 1, 0. Everybody forgets the 0 option. Yeah. All right. Anything else from homework before we get into...
Yeah, 86.
Oh! What's the formula for the average for what I'm going to call an NPQ problem? I'm going to call binomial, I'm going to call it NPQ problems. What's the average for an NPQ problem? N times P. So we know N, we know P. Okay. Anything else from homework stuff? It's being done, right?
No, because then
No.
there are a lot of problems.
Oh,
Not yet.
no, I know, sure. No, I agree with you. I'm like, wow, that's really honest.
She's the one asking.
She's the one asking questions, so she's making assumptions about everybody else. All right. If there's nothing else from 4, let's get into 5. 5 itself, after we discuss it, should be easy. So let's get into it. The first time we're going to look at it is going to be a little freaky, but how many distributions of data do we know so far? We know the normal distribution. We know the binomial distribution. We know the just random, just give me x, p of x, or give me a list of data, right? That's just general who the shit knows, right? So now we're going to start getting, in fact, what's true about the binomial distribution? Is it discrete or continuous data? Binomial. What were we just talking about? People calling the hotline, the medical advice line. Is it continuous or discrete data? Discrete. You're not going to say 1.82 people had the flu. The shit happened.